All right, here we go. Question number 60 from our Calculus 1, homework number 3 in WebAssign. It says a graphing calculator is recommended, not required though, so we're going to see how far we can get without it. The motion of a spring that is subject to a frictional force or a dampening force is represented by this equation, S of t equals 4e raised to the power of negative 1.5t, all of that times sine of 2 pi t, where s is measured in centimeters and t is measured in seconds. Now, before we do the first part, which is find the velocity, I'd like you to notice that below that, they want us to graph the position function, which is what s of t is. And so we have some graphs to pick from. What we're going to do is see if we can get a graph without using a graphing calculator. So let me introduce you to the Casio ClassWiz. It has a table feature which will generate ordered pairs for us that we can plot on this graph. So if you go to menu, you simply need to go down until you find the table function, which is number 9 on the keypad, and then you can enter your function. Notice it has to be in terms of f of x. So we would say 4e to the negative 1.5x. Instead of t, we're going to do x, and then we're going to move down and put sine of 2 pi x. And we don't have another function, so we're going to hit equals to bypass g of x. We want to start at 0 because it doesn't make any sense to talk about t being negative. Time starts at 0 is the initial time, and we want to end at 2. That is the restricted domain for this function that they want to look at. The step is how often you want it to give you points. So if I say step 1, it's going to show me 0, 1, and 2. If I say step 0.5, it'll give me values every 0.5 units. And so I think 0.5 is pretty good, but to get a really accurate picture here, let's say 0.25. And so that'll give us, what is that, 3 points in between 0 and 1. Hit equals, and it's hard for you to see, I bet, in the video. But that says when x is 0, y is 0. So we can put that point on our graph. And then at 0.25, which would be a half of a half, we're at 2.75 high. So if I say that this is 1, 2, 3, maybe, we're at 2.75. And then at 0.5, we're at 0. At 0.75, we would be at negative 1.3, approximately. So that's going to be about here. And then if I scroll down on my calculator, one is back at 0. 1 1/4, that would be here, is 0.6 approximately, so not far above the x-axis. 1 1/2, we're back at 0. 1.75, negative 2.3 approximately. So we're getting really close to the x-axis. And then at 2, we're back at 0. So I don't know if you can see this, but what we've got here is sort of a wave that's bouncing back and forth. Here you go. And this is not necessarily the peak of the wave. I'm just giving you an idea of what it looks like here. That is going to do something like this, and then the farther we go over, the more it dampens. So if we looked at as t goes to infinity, eventually we would just be hugging the x-axis, okay? So now that we've got this representation of what we think the graph looks like, we need to go and see if there is a graph to choose from that looks similar to this. And obviously the first one doesn't look anything like that. In fact, it doesn't start at the origin. The next graph doesn't start at the origin. The next one does, but it goes down first, not up first. So I'm hoping there's a fourth option. Ah, there it is. That looks like what we drew with the corresponding x-intercepts. And so I'm going to have to go with that as my option for the graph of the position function. So now that we have that graph done, let's go ahead and answer the question where it said, find the velocity function after t seconds. And I don't know if you recall, the velocity function is the derivative of the position function. So we're going to have to take the derivative of this function. What I notice is that we've got this first factor in terms of t times this factor that is also in terms of t. And so that indicates that we're going to have to use the product rule to find this derivative. All right, so let me blow up my workspace just a bit. We're going to do the product rule, which says you take the derivative of the first times the second. So we're going to have to take the derivative of 4e to the negative 1.5t. So since the exponent is not just t, since it's negative 1.5t, we're actually going to take the derivative of the exponent first. That's going to go into the coefficient. That's going to come out front. So the derivative of negative 1.5t is just negative 1.5. That's going to be multiplied by 4. And then e to the negative 1.5t. And then that's going to be multiplied by the second, sine of 2 pi t. And then we say plus the first times the derivative of the second. And the derivative of sine is cosine, but we're going to have to multiply that by the derivative of the angle, which is 2 pi. So that'll be 2 pi cosine of 2 pi t. All of that stuff is the derivative. Now, if at all possible, we might want to try to simplify this just a bit. What I notice is that I've got 4e to the negative 1.5t in this term, and I've got 4e to the negative 1.5t in this term. So I'm thinking I'm going to factor out, let me do that in white. I'm going to factor out 4e to the negative 1.5t out of each one of these factors. Okay, so that's gone. And that would leave me with negative 1.5 sine of 2 pi t. And then if this is gone, because I factored it out, that's going to leave me with plus 2 pi cosine of 2 pi t. And I think I'm going to call that good as far as finding the derivative, as far as finding the velocity. I hope they don't ask me to input that as a function. Oh my gosh. And so they do ask me to input that as a function. Yeah, dude, that was not fun at all. But let's see if I can show you what I've done here. I've got my 4e to the negative 1.5t in front of the parentheses. And then what I did, instead of having to say negative 1.5 sine of 2 pi t plus, what I did is I put the 2 pi cosine of 2 pi t first, since it was positive, and then I could just say minus 1.5 sine of 2 pi t. And let me tell you, it's going to really suck if that's not right. So I've got my graph here, and then notice the last thing they want me to do is graph the velocity. What I wanted to show you is that we can actually graph this function as in Desmos, giving us our visual representation of the original function. But then here's the cool thing about Desmos. If you input that as a function and you want the derivative, you can simply say with this notation, d over dx, the derivative with respect to x of f of x. And the green graph, here, let me turn the blue one off. The green graph, that actually represents your derivative graph, okay? So notice that it's going to start above the x-axis, and it's going to come down and go below the x-axis. So for the velocity graph, we need a graph that starts above the x-axis, and it was pretty high, and then it comes down to below the x-axis. That's above 20. Let's see, does Desmos give us that? If I change my range, yeah, that's actually above 20 there that it goes. So I'm feeling pretty good about this answer here. Now, if you're wondering how would we get that without actually using Desmos, what you can do is go back to our answer for our position equation and remember that the slope of the tangent of the position function, those are the y values of the velocity function. So we can see that these slopes here, like up to about a quarter, the slopes are positive, and at the beginning it's really steep. And so a steep line would indicate a large slope, which would indicate a large y value on the velocity graph. And then what happens to the slope of the tangent at the hilltop? Well, it goes to 0. Remember, that corresponds to the y value on the derivative function. And so somewhere around a quarter, we would expect an x-intercept, a y value of 0. And then as you move past that, notice that the slope of the tangent lines would be negative. Not very much at first, but they get steeper, and the steeper negative it gets, that would be deeper under the x-axis. The steeper the y, the steeper the slope, the deeper the y for the derivative. And so that corresponds to what we see in this graph. Really large values at the beginning, the slope of the tangents are large, but the slope of the tangent decreases until we get to about a quarter, where the slope of the tangent goes to 0. And then, like I said, the y values get deeper as the slope of the tangent gets steeper. I love that that rhymes. Let's check that. And then the only thing that I'm really concerned about getting wrong here is this velocity function. Whew, okay, so let's click submit and see how we did. And it counted it right. Awesome. All right. So that's going to do it for this particular problem. If you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.